has several has several research centers around the world. We have one in New York, in Switzerland, and as you heard earlier, in India, China, and we're also in the process of building a research facility capability in Brazil as well. So this is where I work and where Jane works, and I'd like to begin by giving you an overview of why am I here. I'm here basically to try to explain to you some of the work that we're doing in an area that we call computer curation. It's sort of the ability to do text and image analytics and to see how we can use this to enhance our ability to understand the scientific literature and why it is important to you. I hope that's what that says. The idea is to transform information into something that's of value to you. And so, to start with, I thought I would begin by defining the problem. So, in my opinion, this slide says everything about the problem. It's, what I say is here we have too much content and not enough discovery. Every day, papers are published, patents are issued, journals are published, and to be honest, we cannot keep up with all of the information that we should really have be able to read and understand. It's completely overwhelming. So the question is, can we use computers to actually read the documents and to identify the critical entities that are important to us and to do meaningful associations between those entities and other terms, and to basically enhance our ability to understand the information of value to us. So what I'm going to do today is take you through a quick tour of the technology. I'm going to try to give you an overview of both the image analytics, well, the text analytics first, and then the image analytics, because we do both. And then I'm going to spend quite a bit of time giving you a demonstration of how we use the information that the computer reads for us. So this is a picture of a patent. Now, why do we start with patents? The reason why is, well, two things. One is, according to IBM research and IBM's legal department, patents are probably the most important corpus of information that's available to the scientists today. The idea is, or the thinking is that approximately, and it's a guess, but we think about 60 to 70% of all the information published in patents never really gets published in scientific journals. And all the big companies and universities, if it's important work, it usually gets patented first before it ever gets published. So all the big companies like Pfizer, Novartis, and all the other IBM, you have to patent your invention first, and then it gets published. So, and the other nice thing is patents are open source. They're public domain information. The whole idea behind a patent is the inventor puts the information into the public domain, and in return for making it available, then he has a 20-year exclusivity where he can actually take economic advantage of the work for a 20-year period. And this changes from country to country, but more or less. So we consider patents to be very important, and number two, they're publicly available. And so we consider them open source, easy to work with. Now patents have information, and I talk about chemical information, but to be honest, it could be for biological information, engineering information, other types of information. But because I'm a chemist, I focus primarily on chemical structures and chemical information. And patents contain information as text, and they also contain information as bitmap images. So what we do is we try to do an analysis of both the text and the image. So here's an example. This happens to be a piece of a Novartis patent. And if I were to ask the people in the room, you know, what is this compound? Those of you who are even knowledgeable of chemical nomenclature would sometimes find it difficult in order to tell you that this compound is in fact that molecule. And so not only that, but here you notice that this A is not part of the name. So the computer has to figure out, where the name is and where the name is not. And what we've done is we've worked together with a group of pharmaceutical people and people who have domain expertise in this area. And this is not just my work, by the way. It's the work of many, many people. And so the idea is to have the computer read through the documents and automatically be able to understand where the chemical name is and convert it immediately into the structure. And to give you an idea, we've been able to benchmark the ability to do this. We can process about 1 billion pages in 3 hours. So we can take a huge amount of data, the computer can read through it, and we can identify all the chemical names and convert them into structures. The problem is further complicated by the fact that there are synonyms. For example, there's a drug called Valium. Valium is a trade name, but it also has a generic name, and it also has a chemical abstract registry number, a unique identifier, and it has a chemical structure. But depending on what country you're in, Valium has up to 149 different trade names, depending on what country you're in. In addition to those trade names, Valium also has several different what we call IUPAC names. These are International Union of Pure and Applied Chemistry. These are the international nomenclature. And so each of these names, depending on your knowledge of chemical nomenclature, can more or less be correct for that particular structure. So the problem is that the scientist, he simply wants to find information about Valium. But the information is published in a Medline article under the word diazepam, setapam, or some other name. It's also published in patents using one of those IUPAC names, or it's referred to as a chemical abstract registry number in a chemical database. And so we simply want to normalize this. We want to make one query and find information about Valium regardless of how it's named. So this is in Portuguese. It's supposed to say that chemicals have a wide variety of formal and informal names, and often synonym expansion is insufficient, and that if we had the structures, it might be a lot easier for identifying the chemical names. Oh, there we go. Searching by structures could be quite helpful. The other reason why this is important is that if I show you these two molecules, this molecule is, we call it toluene, is a common name, and this molecule is methyl naphthalene. Now, if you were to use a text search engine, you could not find the similarities between those two structures. But if you actually have the chemical structure itself, then you can go into the big corpus of information and you can cluster the documents, not based on the text, but based on the chemical structure itself. And so, by having the chemical structure, you have many advantages on finding similar compounds. So this summarizes, and later on we can go into detail on how this works, but we do what we call text analysis, image analysis. We also analyze the XML files, and we analyze something called complex work units. Complex work units, let's just skip them for now, but if you want we can go into details about what they are. But they're basically the electronic format of the originally generated document. So for instance, if it's a mathematical formula, a complex work unit could be the mathematical formula, the equation in Mathematica, or it could be the actual CDX file if the molecule was drawn in ChemDraw, or a mol file if it was drawn in IsisDraw. So how do we do this? Well, so I should say that this project is an interdisciplinary collaboration between people who are chemists, computer scientists, and a number of other disciplines, programmers and so forth. So mathematicians as well. So for the text analytics, we use 3 different technologies. One is called HMM, which stands for Hidden Markov Models. The other is called CRF, which stands for Conditional Random Field Theory. And the third is called Context-Free Grammars, which is a way of using grammars to selectively identify a particular type of entity, whether it's a chemical name, a disease name, or a protein or a gene. We also have another way, which is based on a very simplistic approach, where we use dictionaries. Now, in a typical search engine, such as Google or one of these other search engines like Lucene or whatever, they work by creating what's called a stop word list. A stop word list are things like words like and, the, for, these trivial words. And what they do is they remove these trivial words so that you only have the critical words in the document. And then they index that critical word to create what we call an index. Well, we had this bright idea of what if we were to use the entire English language dictionary as a stop word list? For example, you take the Oxford English Dictionary and you simply say, if this is let's see if I have a pointer here. If this is a paper, and these are words on the paper, and you simply feed each word one by one, and if that word is in the English language dictionary, we simply remove it from the paper. Well, if it were a novel, then you would end up with just a blank piece of paper. But in the case of complicated chemical names, words like toluene or methylbenzene, they're not in the English language dictionary, so they'll simply pass through this filter, and they'll get passed through, and then they get isolated, and then they can be post-processed through a name-to-structure program into what's called a smile string, and then into a 2D structure. Well, this is a very clever, quick way of doing filtering of chemical words. The problem you run into is you have things like acetic acid, and words like acetic acid, acid's going to be in the dictionary, the English language dictionary. So you have to build a second dictionary. And in this second dictionary, you subtract the second dictionary of words that you want to stay, and you subtract the second dictionary from the first. And then anything that you put in the second dictionary will pass through. And so this is a way in which we can also accommodate synonyms and homonyms and things like that. Certain types of terminology. Oh, okay. Oh, yeah. Fantastic. Okay, so we also have this other approach where we use a whole family of dictionaries in order to quickly filter and identify entities. So once we take the document of interest and we filter out the words, we end up getting the chemical name, and in this case we get the word toluene, and we also get the word methylbenzene. Well, both of these will pass through a program called the name-to-structure program, and that converts the chemical name into a machine-readable format for that chemical. And in this case, it's called a smile string.